Section 3.2. Today we're going to talk about how to write the equation of the exponential function from a table and a graph. We're also going to discuss transformations and the natural log. First, write the exponential function from the table of values. In order to do this, we start at the right and we divide in order to find our rate. So 36 divided by 12 equals 3. Then I do 12 divided by 4. That also equals 3. And 4 divided by 4/3, which also equals 3. So that tells me that B is 3. A is my initial value, which happens at 0. So A is 4. Then I can write my function, f of x equals 4 times 3 to the x. And there's my table of values. If we move on to the next one, and you can check because we know that our rate has to be larger than 1 because our function, as it increases, as it goes up on the x-axis, the y's also have to increase. Second example. Here, once again, we start at a bigger value, so we start at 2, and we divide our way up. Divide, divide, divide. And we find that B equals 2. A, recall, was what happened at 0. So A equals negative 1/5. So my function becomes f of x equals negative 1/5 times 2 to the x. Here's our next example. At this time, you should be answering a question from Educanon, and it will ask you to pick the answer for the function for this example. This is a student example. Now, we are going to move on to how do I write the equation from the graph. Remember on our table of values, we started with the largest value, and we divided by one that was underneath it as far as the x-coordinates go. So when we divide here, we essentially, by looking at the graph, have a table of values. We know A is what happens at 0, and in this case A is 1. And B is our rate. When we do our rates, we take a look here, and we are going to divide from 0 to negative 1. Divide here, so I'm doing 1 divided by 0.5. 0.5 divided by 0.25. So here I see that B equals 2. So my function is f of x equals 1 times 2 to the x. Or simply just 2 to the x. Let's try another one. Write the equation from the graph. Once again, I'm doing the same thing. I'm going from 0.2 backwards, so I see A is 1. So 0.2 divided by 1, and then 1 divided by 5, and I find my B to be 1/5. So f of x equals 1 times 1/5 to the x, or simply 1/5 to the x, because A is 1. In our next example, here, I do the same thing. Only difference is I'm going to notice that A in this case is not 1. A is 4. When I do B, so I'm going to take 2 divided by 4, and I find B to be 1/2. Which should make sense because it's between 0 and 1, and the graph looks like a decay. So f of x equals 4 times 1/2 to the x. The next example, you're going to go through and you're going to answer a question in Educanon. Here's a look at the graph. Please write the equation from the graph and answer the question. Next part of today's lesson is to talk about describing transformations and stating the domain of the functions. For our exponential functions, you notice every parent graph is actually going to be different because it depends on what we use for B. Since x is in the exponent part, then instead of being the original part for our parent, that changes things a little bit. So I have to tell you essentially what the parent graph is to start with. So we see the picture of y equals 3 to the x. And for our example, we want to describe the transformation, state the domain of 1/2 times 3 to the x minus 2 plus 1. A lot of our normal transformation rules are going to apply here. So you'll notice, first, that the plus 1 is on the outside. Anything on the outside is vertical, so that tells me that my graph went up 1 from the parent. The next thing is that I have x minus 2 in the exponential part. This is like having it inside of parentheses. So anytime I'm inside of parentheses, I have to do the opposite. So this also, once again, tells me that it's a right 2. It's with x, it's essentially in the grouping symbol, so that's what's happening there. Lastly, I have this 1/2 being multiplied on the outside. Remember, all things on the outside are vertical, so this is vertical. And then to decide if it's a stretch or shrink, I look at the value. 1/2 is between 0 and 1, so this is a vertical shrink of 1/2. And that is my transformation. Now I need to state the domain of the function. Well, when I look at my exponential functions, okay, as you can see from the original parent graph, alright, I'm sliding this guy left and right a little bit. I'm moving him right, moving him up, but is that going to change all possible x's? No, not really. So my domain in this case is -infinity to infinity. And it will actually be that way for the vast majority of your exponential growth or decay functions. Let's go on to the next example. Here we see a decay graph. Same ideas apply. All of my normal transformation rules occur. So I have a vertical stretch of 4. I went down 5, and because the negative is with the x, this is a reflection over y. And there I describe my transformation. My domain, as you can see from the picture, is still -infinity to infinity. And that's what I did with my exponential functions. Here you can also see why I talked about that there's infinitely many parent graphs for exponential functions. Because all I have to do is change my rate for b. Right? Now, the inverse of an exponential function is a log function. And the log function has some interesting properties. Because it's the inverse, and when we think about domain, we want to think about the range of the original. Okay, so this is a graph of y equals the log of x. I need to describe my transformation, all of which still happens exactly how all of my rules have already been. So the negative is a reflection over the x-axis. 3 is a vertical stretch of 3, and the 4 is going to move me to the right 4. Well, in this case, for the original function, my domain would be 0 to infinity. Because on the original function I can see that there's this asymptote at 0, and I'm only including these types of things. Well, I shifted this guy to the right 4. So instead of crossing here at 1, 0, my new graph is going to cross over here. It's going to do the same things, okay? I didn't go quite far enough. My new graph is going to shift 4 to the right, so it's actually going to cross at 5. and then it's going to get really, really close to 4, but it never actually gets there, because I cannot take the log of a negative value. So logs are similar to square roots, and that what I plug in cannot be 0 or negative. So because I can't take the log of 0, 0 is not included. So here, when I'm talking about my domain in this case, my domain is from 4 to infinity. And that's the domain of that function. So paying attention to your translations will help you with the domain for these. Here, similarly, we have a vertical shrink of 3/5. We went down 3, and we moved left 1. So going down doesn't necessarily affect us, but the left 1 does. So my domain goes from -1 to infinity. Because -1, if I plug it in, would give me 0, and I can't take the log of 0 or a negative number. The next example, here's 2 examples for students to do. Please describe the transformation and state the domain. In this case, I'm just going to have you pause the video, answer the questions, and then come back and check your answers. Check your answers, and we'll move on to the next example. So the next thing we're going to talk about is the number e and the natural log. E is a number just like pi is a number. It's called the Euler number after its discovery by Leonhard Euler. E is a specific exponential function. If I have a times e to the x, it's a growth. And its domain, just like all other exponentials, is -infinity to infinity. Its range, however, goes from 0 to infinity, like all other exponentials. If I have a decay, it's a times e to the negative x, which you'll recall is a reflection over the y-axis. So its domain is still -infinity to infinity, and its range is still 0 to infinity. So e is a number like 3 is a number, 5 is a number. We treat e just like any other number. So it follows all the same rules as exponential functions. The other thing we have is the natural log. ln is the natural log, and this is a log with base e. Okay, instead of having a log base 10, or log base 5, or log base whatever, we use log base e. And ln is the inverse of the exponential function. Its domain, remember the domain on inverses is the same as the range on the original, so its domain is from 0 to infinity, which is similar to our common logs. The range, however, is -infinity to infinity. So we're going to talk about the transformations of not only exponentials and logs, but of e and the natural log. Here are the graphs of e and the natural log, and you can see that my domain, it extends from -infinity to +infinity, but up and down on the y for my range, I start at 0, and I only go up. Same thing here, nothing happens to the left of 0, so my domain starts at 0 and only goes to the right, whereas my range starts at -infinity and goes up to +infinity. Describe the transformation, state the domain. All of our normal rules apply. They apply to these just as they do all other exponentials and all other logs. So as I go through here, this first 2 gives me a vertical stretch of 2. Next, I have a reflection over the y-axis and a horizontal shrink by 1/2. And then I went up 1. And my domain stays negative infinity to infinity. Okay, next example. Very similarly, I reflect over the x-axis because of the negative. I have a vertical shrink by 1/2. I went right 3 and down 2. And this will not affect my domain because I'm talking about exponentials, so it's negative infinity to infinity. Next we have our natural log. Here, my transformations, if you haven't figured out, describing the transformation is exactly the same as all of our other functions. Reflect over x, vertical stretch of 2, and then I went left 1. So now when I talk about my domain, my domain's going to go from negative 1 to infinity because it moved left. This concludes our video for today, describing the transformation, staying in the domain. Now you can move on to your homework, which is worksheet 3.2.